Second problem, people did a lot better. The average on that one was, 83% on the second problem. Okay. So to get started here, right? I want to point something out. So I graded them all, right? I graded 97 of them yesterday. Went through them, and it is pretty. I kind of look at it. I studied a little bit. I try to help you as much as possible, and then I give you feedback as much as I can, and then I move on to the next one, right? So I move through these things pretty quickly. If it's too messed up and there's too many things and the problems hard to follow, your process is hard to follow, and it's hard to follow your math. I'm not going to spend a bunch of time tracking down exactly what was wrong, right? You put a negative in here in your calculator and you should have put in a positive, right? I'm not going to track that down, right? That's going to be on you to kind of find it here. Maybe it is something simple. Maybe the way you did it, it was just missing one little component, but really you were really close to the right answer. That's fine, right? And so I would ask that you do a regrade request, right? And in that regrade request, just explain to me what happened, right? Oh, look. Here's the deal. I got all of it. However, there's this one part that, I put in a negative instead of the positive, and this is, I did a poor job. Really the right equation was there, but you got, so do that, okay? But also be somewhat respectful. I had several yesterday, student posting. I got 4 or 5 that came at me pretty hard, okay? Like attacking me. All right, I get it. Okay, I know it's your grade, it's your livelihood and all that stuff, but keep in mind, I'm on your side here, right? My job is to teach you this material, right? I would love every single person in here to get the material, to understand the material, that when I give an exam, right, that you would show me that you know the material. That's great, right? I want that. That is my number one goal. I'm not out to get you. Right? I think there's some professors out there that really take pride in failing a lot of people. I don't like to fail people, right? I don't like to get you, right? I want you to understand. But also keep in mind, I'm tasked with determining whether or not you're getting the information, that you're making sure that you do in fact understand this material that I'm giving you, that you are picking up what I'm putting down, that you are smelling what I'm stepping in, right? That's my job, right? And then also, I don't have you looking over my shoulder saying, this is what I meant. This is actually what I meant, right? I know I wrote that, but I really meant this, right? I don't have that. All I got is what's on this page. What you put down on that page, that's all I have to determine whether or not you know what you're talking about, okay? So if you do this, again, please do. I encourage it. Actually, it's part of the learning process. Request a regrade request, but also do it if you think you truly deserve it, right? Not be like, well, I'm going to submit it anyway just in case. But if you really are I really think I deserve it. Do a regrade request. But then also just don't just be I think I need more points. Come in here and explain to me why it is you think, right? In a nice professional voice, right? And acknowledging that we're on the same team here, right? Now, don't come at me. I didn't like that. I was whoa, don't do that, right? I'm with you, okay? I'm on your team. Okay, so some key things, right? High, 105. Somebody got it all, right? Including the extra credit. Actually, there's several. Actually, a big portion of people did that, okay? Low was a 30, right? And then, like I said, the average was a 74, right? And you can see that there's a clear distinction between the two, right? And then also note, it's not really maybe a bell curve. Maybe a little bit of a bell curve in there. It's just but not really. It's really heavy on the side. And so, right, if you're up here, great, right? If you're down here, start trying it a little harder, right? We're coming for more resources. Again, all right, I'm on your side. We're throwing all sorts of resources at you, right? We have the Learning Center. We have this. My class, obviously, coming to class. I've recorded all my lectures, right? We post all the homework solutions. Just make sure you're diving into all of those things, right? And then also be careful, again, that you're not falling into that trap where you're just grabbing the homework solutions and copying them and not really understanding what's happening and not understanding every single step. Okay, so again, let's go through this one. Right? Let's go through these things from start to finish. I'm not going to post a solution. This is your solution right now. It's me going through this right now. Okay? As indicated in the figure, airplane A is 640 kilometers to the east, right? So 640 kilometers to the east of airplane B, right? And is traveling at 560 kilometers per hour at that angle that you see right there. Airplane B is in pursuit, so B is in pursuit over here, and it has has an angle of 30 degrees and an initial velocity. Oh, this is slightly different. This is a different problem. Anyways, yours reads something slightly different. I changed it at the last minute. Yours, where I give you the velocity of B, in the actual one, I give you the velocity of B, and I tell you to find the acceleration of B such that you hit it. Okay, so that's you can look at your grade scope to see the actual. This is the original one, and I changed. I thought this one was going to be too easy, so that I changed it slightly, and I regretted it significantly. Okay, I regretted it significantly when I went to grade it. Right, this one would be just you take the two velocities, and then you just come up with positions. There is no accelerations. You have the position equations. You set those positions equal to each other and solve. This one is not that much harder, just a little bit. Okay, so in the one that I wanted. That should have been the acceleration of B is what you're after. I gave you the velocity of B, and you're after that, right? And so literally, this is really, really close to an example that I gave in class, right? Example in class, there was that car going down here, and we had the thing shooting a projectile down at a fixed thing, and we had to find the velocity. I mean, that's an almost identical problem. It's just instead of one going straight and one going down, they're both going up. Right, and then that was it. I mean, that's the only big difference in that. Okay, and so I thought this was a very fair problem. Okay, I thought this was going to be a little softball, just like a little toss out there, and which it was. I tossed it out there, and you guys went this. 3 strikes, like immediately, right? Just and almost every one of you. I think there was only 6 people did it right out of 97, which means that's a little bit on me. Okay, because I thought more of you guys. No, I was just joking. But no, but I guess I must have missed something, okay? Because literally, this is what you see is the answer. Is what you see is the answer, right? You come up with the position A as a function of time, right? This is constant acceleration, as this one is. Right? This is straight out of your notes. The constant acceleration. It's the initial velocity times the angle which it acts, so the component of the velocity in the x direction, and then A starts out 640 in head, so this is the x component of velocity, and it starts out 640 in head, so that's the position of A as a function of time. The position of A in the y direction as a function of time is just the y velocity times time, so it's just that component times time. So that's it. That's the position of A, the x and y direction as a function of time. And then you do the same thing for object B. So this is constant acceleration. This is the constant acceleration equation that was right out of the notes, right? A lot of people got close. But what they left out was the fact that acceleration has components to it, right? That acceleration also has, it has to be broken up into the x and the y direction as well, right? And so a lot of people got pretty close where they just left out the sine and the cosine there, and they solved that. But you have to have it in there. You have to have both of those things in there. So that's that. Okay. And so then at this point, you set the reds equal to each other, so the x positions equal to each other. You set the y positions equal to each other, right? And then you solve for the unknowns. In this case, the unknowns is the time and the acceleration of b. So it's 2.2 hours and 355.01 kilometers per hour squared. And again, I think I mentioned this last time, right? A lot of people converted this into meters per second, which if you're doing kinetics where you're relating stuff to forces, you have to be really careful of those units, and absolutely things got to go in meters per second. In this particular situation, it's just geometry, so you can leave it in any coordinate system that you want, right? And so, or any units that you want. Right, and so it was easiest just to leave it in kilometers per hour. Any questions about this one? Okay, there was a lot of trig errors in here. I tried to piece those things out. Right, there was a lot of little messes up with just what was sine and what was cosine, just little things I tried to pick out if it was just a little thing that messed up. And again, the components here kind of threw some people off as well. Any questions there? Yes, sir.
Does this work fit this problem or the problem that we did?
This is the work for the problem that you did. Yep. For the problem that you did. Because this one has the acceleration, the one that was written up above there. All I changed was I gave it an initial velocity and had you solve for acceleration instead of solving for the velocity. Yep. Right? So then the other thing that happened in here when I was grading these things is I saw inside your brains. Right? I saw inside your minds and I wanted out. Right? Some of you, I was just like, oh God. All right, there's some people, they solved it very interesting, right? I think some people got it right where they were like, they drew these triangles and they were like, oh, if it continues on a path, then they somehow worked out distances and then were able to back solve. That's fine, right? I tried to be as accommodating as possible with that, but really the way that I wanted you to solve it was x as a position, x and y of A, x and y as B, both as function of time, and then you set them equal to each other to solve. Okay. No, any other questions to that? Okay. All right, gravitron. 200-pound man is on a gravitron ride at a carnival on which he is rotated about the z-axis as shown. He lies against the cushion for which the coefficient of static friction is 0.4, and they take theta to be 60 degrees. Right? Everybody been on one of these gravitrons? Yeah. Last time I was on one of these gravitrons, I threw up immediately. I threw immediately after getting off of the gravitron. But it's pretty fun, right? I think they're at most carnivals or fairs and stuff, right? And then you just basically, it spins around and then you get stuck to the wall, right? And you can sit up and then I think some of my old friends used to stand up on there because the gravity's pushing against the side, right? I think that's the brand name is Gravitron. Okay. So he's on that, right? So then this is obviously an F equals ma problem. Okay, and so then you stick to the plan, and the plan involves drawing a free body diagram, right? I should also mention this problem was very close, incredibly close, almost identical to a problem in your homework, right? The problem in your homework was the car coming off the off-ramp, right? The car coming off the off-ramp, going around a corner, it was at a slant. This is that problem. The only difference is the man is stuck to the wall as opposed to a car driving around a corner, okay? So then this one, like I said, this one's what you guys did much, much better, right? This one, like I said, it was an average of like 83%, right? So in this particular situation, right, we draw a free body diagram, right? A free body diagram, there's our object, there's our man, he has gravity pulling him down, he's got a normal force acting up perpendicular to the surface, and then this is a key one, is which direction the friction force is going, right? In this particular situation, you're trying to find the minimum so he doesn't slide down, right? So if he doesn't slide down, then that means that static friction would be pushing up on him, right? Because he's right on the verge of sliding down, so that friction would be going that way. As opposed to the second part of the problem, or the extra credit problem, was saying, what's the maximum so he doesn't slide up? And all you do for the maximum so it doesn't slide up is you flip the direction of that friction force, right? And so instead of it going that way, you make it coming down and to the left, right? And that's how you do the extra credit. Several of you solved them backwards, right? They said, and hopefully I think several of you recognized it and were like, oops, I did that backwards, because they determined the maximum was bigger than the minimum, it was less than the minimum, and so like, oh, I flipped that around. So anyways, I gave full credit for that, I think, or just a small deduction if you did that. Okay, so you have that, right? And then to complete your free body diagram, you have to put in your coordinate system, okay? In this particular situation, this is your coordinate system. We have ER pointed back to the middle, and we have K pointed up like this, okay? And then E theta would be into the board, right? And usually when we did these types of problems before, right, we usually looked at it from above, and we drew our coordinate system on here. I did mine ER and E theta. A lot of people did normal tangent, totally fine with that. Right? And then from down from above, K would be coming up, right? So those are the directions that you had to do, okay? Several of you came in and tilted your axes, right? Came in and said, all right, I'm gonna make a set of axes going this way. I'm gonna have a set of axes going this way and this way, which we did in some ramp problems, okay? You cannot do that in this problem, okay? You cannot do that in this problem. Right? You can, as I say, you can do it in that problem, but you got to be careful, right? You have to be careful about where your accelerations are if you do that, right? When we talk about centripetal acceleration is this direction right here. That acceleration is acting back towards the middle. No matter what, it's going back towards the middle. It has to be accelerating back towards the middle. If it's not accelerating back towards the middle, then it's shooting off on some sort of tangent. So they have to accelerate back. So on this diagram, my accelerations would be this direction. So if I tilted my axes, right, I would have to make sure that my accelerations ends up in both those directions, right? So you can't do that. You can. And actually, I believe one person successfully implemented tilting their axes, and they accounted for the fact that the acceleration would then have components in both directions as well. Totally fine, right? And that's it. Again, you didn't have to do it my way, but you had to do it correctly, right? And so there was some issues with doing that. So that was a big portion of people, or not a big portion, a portion of you did it that way. Just gotta be careful about that. All right, some of the forces in the theta direction. Right? There's no accelerations. There is no alpha term. There is no r dot term. The radius is not turning, so then there's nothing happening in the theta direction. At the beginning, there would be, right? When you get on the gravitron and you're sitting there and the thing's getting up to speed, when that's happening, right? When that's happening, there would be an f theta component. There would be something pushing on the person into the page in this case. But right now, that's not happening, right? Because it's at the constant speed already. Okay, so then you look in the r direction, and so you come over to your free body diagram. There's my ER going that way. I've got a component of the F, and I got a component of my friction force, and then I'm going to have a component of my normal force. And so there's my component of my friction force, there's a component of my normal force, and that's equal to the acceleration in that direction, negative mr omega squared, right? So what's left in that. Okay, and then you look in the k direction, which is up and down right there, and so that'd be f theta. So then you'd have part of your friction force and part of your normal force. So f sine 60 plus n sine 30 minus mg. A lot of issues with this. A lot of people didn't track their angles right. A lot of the trig was wrong in this. Okay, you gotta be careful of that. Right. These guys are these are vertical angles, I believe is what they're called. I was teaching my son geometry just last night. If they cross like that, they're vertical, so those two are the same. And then these two have to add up to 90 because they're perpendicular, so this guy ends up being the 90. Right, or you go 60, 90, not 60, 60, 30. Anyways, it's just going to be careful of that. So a lot of people messed up what was, I think they did a lot of sine 60s and sine 60s. So be careful of that. And then the acceleration in that direction is 0, right? That's what's nice about not tilting it. If you don't tilt your axes in this situation, then we know the acceleration up and down. There is none of the mr squared in that because it's perpendicular to it. And so we know that the acceleration in that direction is 0 because he's not accelerating up or down. So that's equal to 0. And so then we also substitute in what the friction force is, just mu static times the normal force, right? And the only unknown in the second equation right there is the normal force, or you just solve that system of equations. And what you get is the normal force ends up being 236.3 pounds, and the omega is plus or minus 1.78 radians per second. Right? This is solving those two equations at the same time. Okay, cool. And then this one right here, like I said, the only difference to do the maximum so they don't slide up is you just flip that friction force. Instead of having it going up and to the right, we have it go down and to the left, and then you just do the same thing. Some of the forces in both directions and simultaneously solve those equations. In order to get the full credit or to get extra credit at all, you had to get the exact answer. Right? I did not, even if maybe you set it up right, but you put it in your calculator wrong, I didn't give it to you. I just looked for these two numbers, right? 1302, 0.12 pounds, and then omega 5.28 radians per second. And then there was even an additional part that said, is there anything wrong with this? What's the problem with this? Yeah, fast, but what's the biggest thing? Yeah, that normal force, 1,300 pounds, right? So that guy would, at that velocity, at that omega, that 200-pound man would be feeling 1,300 pounds of force, right? So that's 6.5 G's is what they would be going through. 6.5 G's as they're whipping around, and so they'd be stuck to the wall with 6.5 G's. You would survive that. Yeah. You would probably maybe pass out. You might be okay though. I don't know. We'll have to look into that. I think, right, there's lots of G-force videos online, but right, how much that you can see how much you can withstand. I think you'd be okay. It depends on how long it went. I bet you just short periods of time you could handle that 6.5 Gs. If it was prolonged, you'd run into some problems. Okay? Any questions about this? Any questions? Any questions? Any questions? Again, dude, I welcome it. Come. Don't come at me. I said, don't come at me. Just approach me politely and say, hey, could you look at this for me? I think that there was a bit of a mistake, right? Or I think that you were a little harsh on here. Could you help me out? This is the reason I think that I should receive more points, and I'll accommodate the best I can. But then again, also, right, I do have to judge whether or not I think you're picking up the concepts. Okay? All right. We're almost at the end of particles. All right? So what we just derived last time. So side note, we gotta go through this process in a week from Friday. We're doing it again. Okay? We're gonna do it again. That one, a week from Friday is gonna be a work energy problem and then an impulse momentum problem, right? This last homework, basically, that is where it's gonna stop. Okay. Where we're gonna use this impulse momentum stuff is for impacts and collision. Okay, we're gonna start, we started with F equals ma, right? And then we integrated with time. And then we went through and we quickly came up with this: forces acting over time cause a change in linear momentum, right? So this F dt right here is considered an impulse. Forces acting over time is considered impulses. A linear impulse. So a linear impulse causes a change in linear momentum, right? And so we defined what an impulse and linear momentum was. We had a discussion about how if you increase the amount of time, you still have the same net impulse. But then in these two situations, you have the same net impulse, so they both cause the same change in velocity. In this particular situation, we have a big dt, so the forces go down. And then down here, we have a small dt, so the forces have to go up, right? And this is a concept that we see all the time with like airbags and crumple zones in cars and stuff, right? The crumple zone is there to increase the amount of time to slow you down, which then decreases the amount of forces that you have, right? That decrease the amount of force your face hits the windshield, right? Okay. That was a big discussion about that. But then what we got into a little bit later was this conservation of linear momentum. When you have conservation of linear momentum, it's when your net impulse is zero, right? And that's either your forces are zero or, they push one direction and come back the other direction. So as long as those net impulse is equal to zero, right? If it's just a particle, when there's no forces or net impulse, it just means that the object will continue in motion and there's nothing fancy there. But where things are more interesting is when you have system of particles. So you have two objects that are slamming into each other, right? And they're going to have equal and opposite forces. And what those forces do to each object is they cause a change in linear momentum. Okay. But then we kind of added that up and we're able to show that you can that because these things cancel each other out, then what you're left with is just the changes in linear momentum. And then what we're able to say is that linear momentum is conserved across a collision, right? Which is, again, magical that this happens, right? That no matter what, no matter how much energy is dissipated across that collision, no matter what, linear momentum is conserved, which always just blows my mind that works, right? And then you can even use this to calculate how much energy was lost in a collision. You could look at the energy before and the energy afterwards, and you'll see that there's a difference, and then you can calculate it. To me, this is somewhat magical that this happens, okay? And then we talked briefly about oblique impacts, right? So basically this works for oblique impact. We also talked about how we have too many unknowns in this equation up here, right? Usually what you know is the velocities going in, right? And then you have two velocities coming out, and then how are we able to interpret what those two velocities are? We have too many unknowns. And what comes into play there is this coefficient of restitution. The coefficient of restitution is just how the collisions between two objects relate to each other, right? And so, it's empirically derived, meaning that you just throw things at each other and then you measure how they respond to each other, right? So if two steel balls are coming together, they're going to be a more elastic response, not a perfectly elastic, but more elastic. But if you had two lead balls thrown at each other, then it's going to be more plastic, right? Or if you had something thrown at something else with Velcro, right, and the Velcro stick together and they move together, okay? And so let's do a problem like this. And for the most part, I think maybe one homework problem you have to use coefficient restitution. The rest of them are going to be like this, where we have two objects slamming into each other and sticking together. When they stick together, and they move together afterwards. Okay. So let's do this. A 10-pound package starts at rest and slides down a frictionless chute onto a 20-pound cart. And so this comes whipping down, slams into this cart, and then comes to rest after distance d. So the two of them then move together, and then they come to a distance d. And so what we're asked to find is that distance d. Okay. So like I said, these problems are kind of work energy and impulse momentum together. So usually what I do is I come in and I'll label stuff. I'll say, yep, this is going to be state 1. State 2 is right before the collision. State 3 is going to be right after the collision. And then state 4 is at the end there. Okay. And then our first time through will be as complete as possible. And sometimes I go over here and I'll say, yep, 1 to 2. 1 to 2. Right, is going to be a work energy problem. Okay, because it's going from one state up at 1 down to 2. There's no collision that's happening. Okay, 2 to 3 is going to be impulse momentum. That's the collision. 3 to 4, work energy. Okay, just got to lay out how we're going to do this. So then I'll come down here and we'll label 1 to 2. That's the first one we're going to do, 1 to 2. One to 2. Like I said, that one's going to be work energy. So there, we're going, this is our work energy equation. Right? T1 plus V1 plus work done from 1 to 2 is equal to T2 plus V2. And technically, right, if we were following the process, you would do a free body diagram and identify non-conservative forces and do a bunch. But for this, it's just so many steps involved. I'm going to kind of step to that. We're also getting better at these types of problems, right? So we don't have to start as far back. Okay. We'll trust ourselves. When we first learned them, we were going to do all those steps. But right now, I'm not going to do all those steps. Okay, so then at this point, we can cross out a bunch of these terms. T1, so that's the kinetic energy at the beginning, right? This package starts at rest, so there's no kinetic energy at state 1, right? Is there potential energy at state 1? Yep, that's the mass times gravity times height, right? I guess we should probably come in here. We'll call this Y. Two is equal to 0, and Y1 is equal to 8. All right, just to make it clear where we're picking our datum. Right, we could have made the top 0, and then there would be no potential energy here. But I'm going to make the bottom 0. Okay. So there's potential energy. Is there any work being done? Right? In this case, there's no friction. There's no friction on this thing, and then there's no other external forces acting on it. A normal force would be there, but it never does any work, so there's nothing there, right? So there's no work being done from state 1 to state 2, right? And then potential energy at state 2. No potential energy at state 2 because we just defined there's no springs involved, and then gravity, or the height is 0 down at the bottom. And so we're going all potential energy to all kinetic energy, okay? Is the difference there. So we're going to expand this at this point. mg y1 is equal to 1/2 m, is there objects here? I'll call that v a squared. Oh yeah, it is a and b. And actually, it should be more complete. We'll call this MA. MAGY1. It's because the mass of A. All right, we can plug in our values here and determine the velocity. Mass of the object, it's a 10-pound package. Mass A is 10 pounds. So it would be 10 divided by 32.2 times 32.2. Huh? mg is just the weight, but that's fine. And then y2 is 8 feet. Okay. Is equal to 1/2 10 over 32.2 VA squared. Calc this before. It'd be 22.7 feet per second. VA is equal to 22.4 feet per second. And that's not our answer, right? That's just something we need along the way. Okay. Then we go to linear momentum. 2 to 3. 2. 2 to 3. Right? Linear momentum. Right? And what linear momentum is, just says mass times velocity before both objects is mass times velocity afterwards. So MA VA2 plus MB VB2 is equal to MA VA3 plus MB VB3. I'm careful between what states I'm talking about. We're 2 to 3 in our diagram above, before the collision, right after the collision. Again, you cannot say energy at the top is equal to energy at the very end, because there is energy going to be lost across that collision. It goes into sound or heat or something. Okay. We know, so the object B is at rest, right? So that velocity of B2 is equal to 0. So that cart is not moving right before, so that velocity is going to be 0, right? And then there it is, right? I just solved for what this velocity A is, right? And so now I got these two unknowns. This is what I'm showing you that you can't do this, right, without something else, right? I got VA3 and VB3, right? What I do know is it says that they stick together, right? You could add in what your coefficient of restitution is. I think E equal to 0, and then that's, got the equation for that, right? Or you could just say those two velocities are the same. VA3 and VB3 are the same, right? Because they stick together. Either one, you get the same answer. VA3 is equal to VB3, and we'll say that that's just V. MA VA2 is equal to MA plus MB, both of those multiplied by velocity. And I need that velocity because I need to know what it is, the speed of the two coming out of that collision, right? So you plug in our values here. MA is, 10 pounds? Is 10 pounds? 10 over 32.2. 32.2 times the velocity we just found, which is 22.4. 22.4 is equal to 20-pound cart. 20-pound cart. So 30 divided by 32.2. So that's the 10 plus the 20 times velocity. Right. And from this, plug into your calculator, we get my velocity equal to 7.57 feet per second. Again, not our answer. I'll make it more clear that that's a 7. .57. Okay, so it did slow down as it should, right? It went in at 22.4 feet per second, had a collision with the other object, and then it came out moving slower, 7.57 feet per second. Okay. And then 3 to 4 is the last step. Three. I don't know why I was typing those, but I'm doing that today. Felt like typing. Right, back to work energy. So we got T3 plus big V3, potential energy, plus work done between 3 and 4 is equal to T4 plus V4. I would just write that whole thing. Even though you know some of those terms are going to go to 0, I'd recommend doing this. It just helps keep your mind clear and stuff. And then also helps me grade when you're doing your exam and stuff. I could see where your thought process was instead of just leaving stuff out. Right? You may have made an assumption. All right, so this thing does have kinetic energy coming in, right? Because I just solved it has some velocity that we just determined, 7.57. So it has that. How about potential energy? No, right? It's at 0 and it's staying at 0. There's no springs involved, so V3 is 0, right? Work being done from 3 to 4. Is there any work being done? Yep, friction's doing work. What kind of work? Negative work, right? On this side of the equation, it's pulling energy out of the system, so it's going to be negative when we get there. How about kinetic energy afterwards? After, like at the end, state 4. Nope, it's stopping, right? That's what we're after, is it's stopping. It's stopping, and then there's no potential energy. It's stopping, right? And so what's happening, right, is the kinetic energy is being eaten up by the work being done, right? That work being done is taking all the energy out of the system, and it's just going to come to a complete stop. Right? So it's okay to have a 0 on the right-hand side, right? So let's now expand it. So this would be 1/2 MA plus MB times V3 squared minus mu K MA plus MB times G, right? So that's MA plus MB times G is the normal force, and then it's multiplied by mu K. And then that's a negative there, right? Because it's pulling energy out of the system. It's acting the opposite direction of motion. And that is equal to 0, right? And then V3 right, goes right there. So if we put in all the numbers, 1/2. I wasn't done yet. I said, what is missing from this? What's missing from it? D, because it's hard to solve for D if we don't have it in there, right? D is what we're after. Thank you. I was just going to, so what's missing? Great job. You get an A for the day, whoever said that, right? I definitely would have been missing that in a second. 10 over 32.2 plus 20 over 32.2 times 7.57 squared minus what, mu K in the picture. Oh, yeah, 0.2. 0.2. 10 over 32.2. That's 20 over 32.2. Obviously, there's shorter ways to do this instead of writing it all out. 32.2. And then D is equal to 0. The only unknown in there is D. Solve for D. 4.45 feet. That is our answer. Okay? So what if I said, how much energy was lost across that collision? How would you solve for that? Across the collision. How much energy was lost across that collision? How do you think you would do that? What's that?
Set that to our original energy.
Yeah, or you just compare it to your original energy, right? You would compare it to your original energy, right? You could just you could do a couple things. You could say, how much energy was at the beginning, right? Here's how much energy was at the beginning, MGH, right? This is my energy at the beginning, MGH, right? And then I could just look at the energy right after the collision, right? And what would be the energy right after the collision? Well, it would be what was happening. It would probably be, you could look at a couple of them. You could look at the kinetic energy right afterwards. Actually, you'd probably look at that. You'd probably look at the kinetic energy right after the collision, right? And then you could see, well, there'd be a difference, right? And there should be a difference because there was that collision happened and there'd be an energy loss, right? Where did that energy go? I don't know. Sound, right? Velcro, I was thinking of these things velcroing together, some sort of deformation when it hits in there, some heat generated or something like that, or sound or something. There's somewhere that's going. And do I need to like capture? No, it automatically, no matter what, linear momentum is conserved, right? I don't really care like where that energy went. It went away, but I can calculate it afterwards, which is pretty cool. At least I think that's pretty cool. Okay. What we'll do next time, and I'll do this one briefly next time, is we'll look at a ballistic pendulum. This is the way they used to measure velocities of bullets, right? Is they had this little thing that it would shoot a bullet into a block, they would embed together, and then this pendulum would swing up, and it had a little ratcheting system, so when it got hit it would ratchet up, and then it would stick at the highest point that it was at. And then based off of that, they could back calculate the velocity of the bullet. And this is how they used to do it. Nowadays, they got these little things that you shoot through, and it like senses the thing they determine the velocity, the muzzle velocity. But this is how they used to do muzzle velocity. It was these ballistic pendulums. So we'll look at this next time. We'll do one last little example. And then, we got 7 minutes, all right. Then we'll do conservation of angular momentum. I do want to, let's at least start this one. We got 7 minutes. I just want to make sure that you have enough examples so that when you're doing your homework, which is due on Friday, you'll know how to have another example here. At least I'll just set it up. Okay. So again, what I always do when I do these things is I lay out how I would solve these things, right? So 1 to 2. So there is, obviously there's the bullet coming in, it's going to strike B, and then the bullet A, and then the thing's going to swing up. So I don't really care about the energy before. It doesn't say anything about like it was shot from over here and then it's coming to this point right here. We're just right before the collision is what I'm after. I'm after the velocity of the bullet right before the collision. So I'm just going to do state 1 is right before the collision, right? And then I'm going to do state 2 is right after the collision, and then state 3, I already have it labeled here, is going to be at the end and how it swings up. Okay. So 1 to 2, right? 1 to 2 is going to be impulse momentum. Right? And so what we would look at is mass A times VA1 plus mass B times VB1 is equal to mass A times VA2 plus mass B times VB2. Right, this is a quick one. We'll get through this one. Right? No velocity of the block before the collision. And then we're also going to make the same, they're sticking together. It's going to embed inside of that block. So right afterwards, they're going to be the same. So VA2 is equal to VA3, which is equal to what we're going to call V. We'll call that V2. What did I do? No, this is 1 and, sorry. That's just a 2 right there. We call them both V2. And B times V2. There's only one unknown. Okay. what I'm after, just highlight what I'm after this, VA1. Right? So right now I can't solve it. I don't know what V2 is. I don't know what its speed is right after the collision. So I can't solve it at this point. So I always do these things chronologically. But there's a lot of problems like this. I always do them chronologically. I'll look at, well, the collision happens first, and then afterwards the thing swings up. It tells us how much it swings up, so I'll need to work that out. And so I can't go any further right here because I don't know V2. So I need to go to the next state to determine what V2 is. Once I get V2, then I can come back and solve for VA1. So let's do the next stage. Ooh, are we gonna make it? We're gonna make it 2 to 3, right, is work energy. There we go. T2 plus V2 plus work done from 2 to 3 is equal to T3 plus V3. Okay. T2, that's what we're after. It's in that thing right there. No potential energy at state 1. I'm going to define this being 0 down here. Or state 2, Y2 is equal to 0. And this is going to be Y3 right there. If I define it that way. And then there's going to be no work being done from one state to the other. There is no external force. There is going to be like tension in this, which is kind of like a normal force. There's no motion in that direction, right? It just kind of swings around. It's just like a normal force. There's no movement in that direction, so there's no work being done. And then kinetic energy, there won't be any kinetic energy at the end, right? Because it's going to swing up and stop. And where it stops, there's no kinetic energy. So it's going kinetic energy at state 2 to potential energy at state 3. Right? Expand this thing. 1/2 MA plus MB times V2 squared is equal to MA plus MB times G times Y3. Okay, Y3, a little bit of geometry to get Y3. I think I'm just going to tell you what it is at this point. It's all based off of this. You look at this little triangle right here. Right. They give you this angle of 6 degrees right here. I know this length that's given to me. I can back solve what that height is, and then so then how much it changes is going to be between this height and this height, right? But I'll let you work that out. This at Y3 ends up being equal to 6.85 times 10 to the negative 4th. And so if you plug in all the knowns there, what you get out of this is V2 equal to 0. V2 is equal to 0.116 meters per second. That's how fast it would have to be going in order to get this thing to swing up the height that I gave you there. You take that V2 and you put that into here, right? And then you solve for what that VA1 is. And what you get for VA1 is equal to 232 meters per second. Okay. That was just, like I said, I always started out chronologically. Like you could do it the other way. You could say, well, I need to know what's happening from 2 to 3, and then I'm going to take that and I'm going to put it back from 1 to 2. I just systematic. I just go chronologically in that order. Okay. I will also say this, and as if I haven't said it enough, is, my God, the algebra. I swear to God, most of your problems were associated with algebra. A lot of your problems were associated with algebra, right? Learn how to use your calculator. It's a gift. This is just like the first glimpse of it that you're seeing in as you move forward, right? As you move forward, you get to use those tools. You get to use those tools, right? And so, right, you see my work, right, on the exam. You saw it, right? And it's really nice and concise, and I just put in all the values, and I said calculator, and I did it. Some of you literally a page worth of algebra, and then you get the wrong answer almost every time, okay? So just learn how to use your tools. All right, break.